Okay, this is a video about some random things I want to tell you. After I looked at your summer assignment and your summer assignment quiz. Okay, on your math for AP Physics C, you had an integral from 0 to 2 of some stuff like this. And, so whatever, you end up with something, t to the negative 2, something t to the negative 1, and then, something t squared. And you're supposed to evaluate it from 0 to 2. So most of you realized, okay, cool. The way you evaluate integrals is you plug into here, and then, or whatever, who cares? The point is that you evaluate that expression at the first guy, but then you subtract that same expression at 0. Uh-oh, what just happened? I blew up the paper. So sad. Okay, guys, you can't just ignore this guy. Take this as an example. What if I wanted to do sine of x dx from 0 to pi? Okay, it's negative cosine x from 0 to pi. So you might be tempted to write just negative cosine of pi, and then I can just ignore the 0. But you can't do that. Cosine of 0 is very much a non-zero number, right? That is 1. That is 0, right? You get 1. So just because there's a 0 down here doesn't mean you can ignore it. You have to plug it in. Okay? That's random fact number 1. Random fact number 2 is about the range equation. Okay, you will find it's like r, and then, I don't know, there's a v squared, there's like a sine theta, cosine theta, there's maybe like a 2, there's a g down here, something like this. This is not a useful thing to use your neurons on, right? You'll find this in books, but what is much more important is that you know how to derive this. So do not ever memorize the range equation, because you're never going to be asked to just give me the range of something, right? You're always going to be asked to derive it. All right, that is random thing number 2. Random thing number 3, mg. What is this? This is weight, right? Also known as F sub g, because it's the force due to gravity. But what is it really? Is this g negative 9.8 meters per second squared? No. It has the same magnitude as that, your favorite little acceleration due to gravity. But this is the gravitational field strength. It's what turns this mass into a weight. It's almost like a conversion factor for Earth, right? Because this g is different for each planet you're on, okay? But it is true that the magnitude of g as the acceleration due to gravity and the magnitude of g as the field strength happen to be the same, okay? But that is only because in Newton's second law, the net force on something in free fall is just mg. Oopsies. Okay, so the net force on this guy is mg. And Newton's second law says that the net force is equal to ma. These are very different things that are happening on each side, okay? This is the definition of weight. This is what happens when you put a mass in a gravitational field, okay? You get a force on it that's equal to this. This is just this Newton's second law part, where this m is the inertial mass. It's the mass that resists that force, okay? It's the reason why if you push on a heavy shopping cart, why you get less of acceleration for the same force. This is the gravitational mass, okay? So this is something that's in Newton's law of universal gravitation. We'll get to that in a little bit. But the fact that those were the same and we could cancel it out and say that the acceleration in free fall is g, this is crazy and so cool. The fact that gravitational mass is actually equal to the inertial mass was a very, very big deal and is not, it's not directly obvious that it should be, but it's very, very cool that it is. Okay, so I just really, really, really want you, when you see g, this is not a negative number. This is a magnitude of the gravitational field strength, so 9.8 or 10, and it's newtons per kilogram. And I like those units much, much better because it really shows you that it's a field. All right, awesome, almost done. On your summer assignment quiz, you had something, that looked like this. And you had to do a Pythagorean theorem to figure out that guy. All right. Now, you should know that the number you're going to get here is going to be very, very close to 350, right? Because 36 pretty puny compared to 350. But you end up with something like 352 meters per second. Sig figs are very important to chemists. They are not important to physicists. We use generally 2 to 3 sig figs and just, where it makes sense. So if you said your answer was 350, that looks a little bit weird, okay? This is where you would want to actually keep that 2, okay? Even if these only had 2 sig figs. We never, ever, ever talk about sig figs in this class. Cool. When doing a free body diagram, you only use variables in a free body diagram. So this is the normal force. This is mg. Let's say this thing's getting pushed. Call that F applied or F push or something. Maybe it has friction. Call it F. If you want to put a little bit more information and say like, that's 220 newtons, that's fine. But if someone asks you to draw a free body diagram, you should not do that. That's not a free body diagram. Okay? So they always have to have the variables. Good. Another point that's important about free body diagrams, and this is, of course, about the elevator problem. So either mg or fg or whatever. When you write net force equals ma, okay, and I talk about this a lot in that video that I keep pushing out to you. This should be just a magnitude. Okay, and then you can, in this case, my A was up. So let me explain this. These numbers are magnitudes, okay, all the numbers in here. There's no hidden negative signs, okay? And so we want to pick the vector that's in the same direction as A, to be positive, and if it's in the opposite direction, I sometimes write FG, sometimes write MG. If it's in the opposite direction, it gets a negative. Some of you did the elevator problem where you talked about the acceleration, you plugged in the number, and it was like negative 0.9 meters per second squared, but you had this as the free body diagram. That's consistent, but it's not useful for your future because very, very, very often, and I might have done you a disservice by putting so many numbers on your free body or on your summer assignment. Very often, we will not ever use numbers, so you won't ever have a chance to put in that acceleration is a negative number. So it's very, very important when we use these variables to just make sure they're always magnitudes and that the signs are outside of that. Hopefully that makes sense. I'm happy to explain that 12 more times if you need to. On the same note, if you wrote something like this, and actually a lot of you are not even making sure you have your net or you could also write net there. Don't just write F, it needs to be net force here. So I saw this on some people's papers. Net force is Ft plus Fg. This is only true if you are actually writing a vector equation, okay? If you do not have these vector signs, then Ft and Fg are the magnitudes of these. Magnitudes are always positive numbers, okay? This is just not a useful equation if you're actually going to do stuff, right? This is that useful equation. And so then in your part B, where your acceleration was down, then you said, okay, my net force is ma. My net force now I should write as mg minus t. And even if you were able to reason through this and eventually write something like, t equals mg minus ma, this is physics. That is math, okay? This physics shows you the net force, okay? That's the interesting part. This is just solving for t. That's just algebra, okay? I am always going to be looking for this, and I am always going to be looking for variables. I'll tell you, when I grade, I basically just look for equations and variables. I give very, very little notice to the numbers that are involved. It's really, really important. Actually, very, very, very many problems in this class will have no numbers at all. Okay, I think that's all I want to talk about right now. Please, please, please ask me questions if you got them.